All right, section 6-3 is on the uniqueness theorem and the properties of your logarithmic functions. And the objective of this section was to use the uniqueness theorem for derivatives to prove that the ln of x, that function we defined in the last section, which is the definite integral from 1 to x of 1 over t dt, is in fact a logarithmic function, and it has the properties of logarithms. And that's the part of it that we have yet to cover. We'll talk about that today. In fact, let's start out with the uniqueness theorem. Here is the uniqueness theorem for derivatives. And we're going to use this to prove that this ln of x function has all of the properties of being a logarithm. And then we'll also use it to prove that, in fact, the ln of x function is the natural log function, that is the log base e function that we know. All right, so the uniqueness theorem for derivatives states the following. It says if, and it has two conditions here. The first condition is that f prime of x is equal to g prime of x for all x in the domain. So you have two functions here, function f and function g, and you have to have that the derivative of each function is the same for all values of x in the domain. And so what that does for you, if you have two functions that have the same derivative, that means they have the same slope everywhere. If they have the same slope everywhere, that means that they are increasing and decreasing in the same spots. But not only that, but they're increasing at the same amount and decreasing at the same amount, or the same rate, at every single point. So the two functions would have the exact same shape. All right, that doesn't mean the two functions lie on top of each other. It just means they have the same shape. They could be one function above the other one and have one with or the same shape, but they obviously are not lying on top of each other. The second condition, though, says that you have to find some point A where f of a is equal to g of a for some value of x equals a in the domain. If that happens, then that guarantees that they share at least one point in common. So now you have two functions that have the same derivative everywhere, so they have the same shape, and they have at least this one point at a in common. And the conclusion then is f of x is equal to g of x for all x in the domain. So they must have every single point in common. If they have the exact same shape and you know that they have one point in common, all the points must be in common. The two graphs must lie right on top of each other. F of x and g of x must be identical. All right, that is a unique function rather than two different functions, function f and g. It is in fact one in the same. All right, so we can use that to prove that two things are equal to each other. Again, we've talked about this before, that if you look at the conclusion of a theorem, it will usually tell you what you can use that theorem for. Sometimes it's not quite as clear, but this one is pretty clear. The conclusion is that f is equal to g. It tells you that you can prove that those two things are equal to each other. So whenever you're trying to prove that two things are equal, you can use this uniqueness theorem to do it. All right? Just to give you an example of some things that you've done in the past like this. Last year in pre-calculus, you were proving some trig identities. And you're proving that one thing was equal to something else. Well, one way that you could have done it, obviously you used trig properties and a little bit of algebra to prove those last year, but turns out you could use the uniqueness theorem as well to do that. Doesn't necessarily mean it's always easier this way, but it certainly is a possibility that you could use the uniqueness theorem to prove that. Prove two things are equal to each other. All right. Let's take a look at a couple of examples here. This first example here is going to have us prove one of the properties of logarithms to prove that our ln of x function has the property of being a logarithm. In fact, it's the product property is what they want us to prove here. Example 1 says prove that the ln of AB, a times b, is equal to the ln of a plus the ln of b for all a and b greater than 0. All right, so prove that the ln of a times b is equal to the ln of a plus the ln of b for all a greater than 0, b greater than 0. Okay. All right, so let's go through the proof of this. And we're going to use the uniqueness theorem for derivatives to help us do that. So the uniqueness theorem for derivatives, first thing it states is that you have to show that you have two functions whose derivatives are the same. So the first thing we're going to do is we're going to define our two functions. And just for ease here, so that I can clearly see my variable in this, I'm going to let x be a in here. All right. So we're going to say that f of x, we'll say that f of x is the left side of this equation here. So f of x is going to be the ln of x times b, where b again is a constant here. X is our variable. And we're going to let g of x be the right side. So we'll have the ln of x plus the ln of b. All right. All right, so we've defined our two functions here for function f of x and function g of x. So now let's go through the uniqueness theorem for derivatives. So I'll call that UTD for uniqueness theorem for derivatives. And there are two conditions, just like we do for most of our theorems when we go to use them. I like to list the conditions here one at a time and just show that we meet each of the conditions, so then we can make our conclusion based on the conclusion of the theorem. So the first part of this is that you have to show that f prime of x is equal to g prime of x. So let's find out what f prime of x is equal to. Well, again, we're talking about f prime of x in terms of the ln function that we defined. So we have already stated that the derivative of the ln of x using that second form of the fundamental theorem of calculus was equal to 1 over xb times the derivative of x times b, which is just going to be b. That's just following chain rule along with the rule that we already know. Of course, the b's here will cancel each other out to give us just 1 over x. All right. Take a look at the second function, g prime of x. So again, this is based on the ln of x at definite integral from 1 to x of 1 over t dt. So the derivative of ln of x, we actually have a sum of two functions, so use your sum property first, but the derivative of the first function, we've already stated, is 1 over x, plus the derivative of ln of b. Now again, b is a constant, so the ln of a constant there is just going to be another constant, so its derivative is 0. So this turns out to be 1 over x as well. So we have the first part the first condition for the uniqueness theorem for derivatives is satisfied here. Turns out that f prime of x is equal to g prime of x. All right. The second condition. The second condition, you have to find some point to plug in. In here, we'll plug in some value for x in this case, and you have to use it to show that f of a is equal to g of a. Now, it turns out that you can technically pick any point, but it's usually easier if you're a little bit more selective, a little bit more careful on what points you pick to plug in there. So I'm going to let x equal 1. Now, it doesn't turn out that x equals 1 is always the value used. It just turns out to be that in this case that we're going to use it, but definitely not every case is going to be this way. But if we plug in 1 into our two functions, f of 1 would equal, again, it's the f of x was equal to the natural log of, or excuse me, the ln of x times b. So this is the ln of 1 times b, which is just equal to the ln of b. And g of 1, remember, is the ln of x, so that's the ln of 1 plus the ln of b. And we've already proven what the ln of 1 is equal to. That's our intercept property. So ln of 1 was 0. So we end up with just 0 plus the ln of b, or that's the ln of b. So in both cases, we get the ln of b. So we have that their derivatives are equal to in each other in the first part of this theorem. In the second part of the second condition, we have that we found a point where they have in common. So now we can conclude, therefore, by the uniqueness theorem for derivatives, f of x is equal to g of x. Or we could say f of x is the ln of x times b is equal to g of x is the ln of x plus the ln of b. And if you prefer, you can replace x with a. So we can say, so the ln of a times b is equal to the ln of a plus the ln of b. You could leave it in terms of x and b. That would be fine as well. But there we go. That's what we were trying to prove. We used the uniqueness theorem to prove that these two things are equal to each other. So turns out that our ln of x function has this property that logarithmic functions have as far as the log of a product is concerned. All right, let's take a look at the second example. And this one says to prove that the ln of x is equal to the log base e of x for all x greater than 0. So we want to prove that the ln of x is equal to the log base e of x for x greater than 0. All right, so we'll go through the proof of this, and we're going to use the same theorem to do this. In fact, the process is going to be very similar. Now, again, remember that this function that you see over here on the left side of this, that ln of x, that's our function we defined in the last section, that definite integral from 1 to x of 1 over t dt. Versus this function that you see over here on the right, log base e of x, that's what we know as our natural log function. Okay? All right, so let's start out by defining our two functions that we're going to work with. So it doesn't matter which one you pick as which side, but we'll say that f of x is the left side here. So f of x is going to be the ln of x. And we're going to say that, oops, I can put that over here. And that g of x is equal to the log base e of x. All right, so the first condition here for the uniqueness theorem for derivatives. We have to show that the derivatives of these two functions are the same. So f prime of x, we've actually already done this. We've already shown that the derivative of this function is in fact equal to 1 over x. Remember, it's defined as the definite integral of from 1 to x of f of 1 over t dt. And so using that second form of the fundamental theorem of calculus, we've already proven this, that this is equal to 1 over x for x greater than 0. All right. For the second function here, g of x, we actually proved this earlier, but I'm going to go through and prove this again. We proved it back in chapter 3, that what g prime of x is equal to here. But let's go through and show you how to do that. That's using the implicit differentiation. I'm going to just for ease here, I'm going to say that y is equal to the log base e of x. We'll replace g of x with y here just for ease of showing this one. So we're trying to find out what g prime is equal to, or that's what y prime is equal to. So if we say that y is equal to the log base e of x, remember that's the same as saying that, just using your definition of a log, that's the same as saying that e to the y is equal to x. Those two mean the same thing. And if we take the derivative of this with respect to x, because that's what we're trying to do, to find g prime of x, the derivative with respect to x. On the left side, just realize when you do this, you've got an implicit relationship here. So on the left side, when you take the derivative, use chain rule. So derivative of e to the y is going to be e raised to the y power times y prime. And on the right side, derivative of x is just 1. And we're trying to find out what y prime is equal to, so solve for y prime. It's going to be 1 over e to the y. And replacing y with what we said it was equal to, y is the log base e of x. And this exponential and logarithmic function are inverse. Actually, I can take that back. I can make this a little bit easier here because we already wrote down what e to the y is equal to. You could continue with this, and e to the log base e are inverses, so they'll in essence cancel each other out, but I can make that even simpler. e to the y we said right here is equal to x, so I can just simply substitute it that way. So we get 1 over x is what y prime is equal to, and remember y was equal to our function for g of x. So we have that the two functions have the same derivative. All right, the second step of this process, or the second condition that we have to meet, we have to find a point that function f and g are equal to each other. So again, I'm going to pick x equals 1. Again, I stress that it's not always going to be x equals 1. Just happens to be for these two that it is, but it will not always be that way. But let's plug in a 1 into both functions and see what happens. So f of 1. Now function f was equal to the ln function, so that's going to be the ln of 1, which that, remember, is the intercept. We've already proven that that's equal to 0 for the ln function. That's just the definite integral from 1 to 1 of 1 over t dt. That's 0. Do the same thing for function g. And for function g, this is going to be the log base e of 1. Remember, we said that when you're solving a logarithm, it's like asking yourself the following question. What power do I have to raise the base e to in order to end up with this value of 1? E to what power is equal to 1? Well, anything to the 0 power is 1. So e to the 0 is equal to 1. So in both cases there, f of 1 is 0 and g of 1 is 0. We got that they share a point in common. So the derivatives are the same and they have one point in common. We can make our conclusion. Therefore, by the uniqueness theorem for derivatives, f of x is equal to g of x. Or if you want to put it in terms of our two functions and what they are equal to, that's the ln of x, our function we defined back in section 2, is in fact equal to g of x, which is log base e of x. The ln of x function is in fact equal to our natural log function. They are the same. All right, and that's as far as we're going here with this section.